Welcome to Lesson 8.6 Production Deployment and Integration. Learning Objectives. By the end of this lesson, you'll have deployed your Linux distribution build assistant as both an interactive terminal UI and a REST API, wired it into real build workflows, and set up performance monitoring. Budget about 90 minutes. This is expert level work, and it assumes you've completed lessons 8.1 through 8.5. Deployment options. The first deployment target is a rich terminal UI, real-time assistance directly inside your build terminal, powered by Python's rich library for syntax-highlighted, color-formatted output that actually looks good in a console. The second option is a REST API built with Fast API. This is the right choice when you need to integrate your assistant with build scripts, CI/CD pipelines, or any tooling that speaks HTTP. The third deployment pattern is automatic error log analysis. The assistant watches your build logs, passes failures as they happen, and surfaces suggested fixes without you having to manually copy and paste error output. That's the full picture of what this lesson covers. Interactive Terminal UI. The Terminal UI script does three things in sequence. First, it loads your fine-tuned model using unsloth's fast language model with load underscore in underscore 4-bit set to true. That 4-bit quantization is what lets a 7B parameter model fit comfortably in your P40's 24 GB of VRAM without sacrificing meaningful response. Second, it drops into an interactive loop where the user types questions. Critically, it also accepts error log context. So instead of asking a generic question, the assistant sees the actual failure output and generates a response grounded in your specific build state. Third, the display underscore response method does more than print text. It parses the output for shell commands, renders them with syntax highlighting via rich, and flags any command it considers potentially destructive with a visible warning. That last detail matters in production. You want a human to pause before running something like rmrf. Two commands get the terminal UI running. The first installs rich with pip install rich. Rich is what gives the terminal its formatted output, colored panels, and syntax highlighted code blocks. Without it, the deploy script will fail immediately on import. The second command launches the assistant itself, Python scripts /06-deploy.py. Watch the startup output carefully. You're looking for confirmation that the model loaded successfully and that the interactive prompt appears. If you see a CUDA out of memory error here, double check that no other process is holding your GPU VRAM. Run NVIDIA shmy before retrying. This command, sudo apt-get install libssl-dev, resolves a specific and common build failure, ocliv/ssl.h, no such file or directory. That error means the C compiler found the OpenSSL library itself but couldn't locate its header files, which live in libssl.ev separately from the runtime package. Installing libssl.ev drops those headers into the right system paths, so the next compile attempt succeeds. After running it, apt will confirm the package version being installed along with any pulled-in dependencies. That confirmation is your signal to retry the build. REST API with Fast API. The Fast API server script follows a deliberate startup pattern worth understanding. The model and token error are declared as global variables but intentionally left unloaded at import time. The actual loading happens inside a startup event handler, load underscore model, which fires once when UVCon brings the server up. The load underscore in underscore 4-bit flag is set here too for the same memory reason as the terminal UI. Watch the console during startup. A FAR model loaded successfully message confirms the model is in VRAM and the server is ready to accept requests. The /query endpoint is where the real work happens. It takes a question, builds a structured prompt, runs inference, and returns a JSON object containing 4 fields: the suggested command, a plain English explanation, a confidence score between 0 and 1, and a safety warning if the command is potentially destructive. The /health endpoint is a lightweight liveness check your load balancer or CI system can poll to confirm the server is alive. 2 commands stand up the API server. First, pip install FastAPI UVCon installs both the framework and the ASGI server that runs it. FastAPI defines your routes and request handling, while UVCon is the process that actually listens for connections. Second, Python script /api-server.py starts the server. In the terminal output, look for a line showing the host and port. UVCon running on http://127.0.0.1 8000. That line is your confirmation the server is. If the port is already in use, you'll see an address already in use error. Kill the conflicting process or change the port in the script before retrying. This curl command exercises the /query endpoint directly from the terminal. A fast way to verify the API is working before wiring it into anything else. The post body sends a question asking how to install Python 3 development headers with temperature set to 0.7. Temperature controls how deterministic the model's output is. Lower values produce more focused, repeatable answers. Higher values introduce more variation. The JSON response you get back has 4 fields to pay attention to. The command field contains the actual shell command to run. The explanation field gives the reasoning in plain English. The confidence score, 0.92 in this example, tells you the model is highly certain about this particular suggestion, and the safety underscore warning field being null confirms there is nothing destructive in this response. If confidence comes back below roughly 0.7, treat the suggestion as a starting point rather than a definitive answer. The ask_assistant Python function is your reusable client wrapper for the API. It sends a post request to http://localhost 8000/query with the question, an optional context string, and a temperature of 0. The function checks the HTTP status code first. A 200 means the request succeeded and it's safe to pass the JSON. From that JSON, it extracts and prints the command, explanation, and confidence level. The safety warning check is the important detail here. If the returned warning field is non-empty, the function prints a prominent alert before displaying the command. That's the behavior you want in any automated workflow. Never silently execute a potentially dangerous command. On any non-200 response, the function surfaces the status code so you know exactly where to start debugging. Integration with build scripts. Build scripts. The animx-build.sh script demonstrates the most practical integration pattern, embedding the AI assistant directly into an existing build pipeline. The script opens with set E, which means any command failure immediately halts execution. Errors can't silently propagate. The API_URL variable points to your local fast API server. The ask_assistant bash function sends a question and context to that server via curl and extracts just the command field from the JSON response. The handle_error function is where the real value shows up. When a build step fails, it grabs the last 50 lines of the log file, passes them as context to ask_assistant, and presents the suggested fix to the developer with a prompt to apply it or skip it. The main build flow then calls lbconfig with your target distribution and architecture, routes any failure through handle_error, and proceeds to lbbuild. The result is a build script that doesn't just fail, it actively helps you understand why it failed and what to do next. The log analysis script takes a different approach from the interactive build integration. It's designed to be run after a build fails against an existing log file. It uses regular expressions to scan for known error patterns, missing files, missing packages, compilation failures, permission errors. That pattern matching step is important because it filters the noise out of a potentially thousands of lines log and hands only the relevant failure context to the model. If no errors match any pattern, the script confirms the log looks clean. When errors are found, it queries the fast API assistant for each one and prints the suggested command and explanation side by side. The output is structured so you can read down the list and address failures in order, a significant improvement over manually greping through a raw build log. Running Python script /analyze-errors.pybuild.log kicks off that log analysis against your actual build output. The script parses the file, counts the distinct errors it finds, and prints a numbered list of suggested fixes with commands and explanations. The key thing to watch for in the output is the confidence score alongside each suggestion. High confidence means the model has seen this error pattern frequently in training data and its fix is well grounded. Lower confidence suggestions are still useful starting points, but verify them before applying. Performance monitoring. Warnings. The monitoring code adds Prometheus instrumentation to the fast API application with 3 metrics. A counter tracks total request volume. A second counter tracks errors specifically, labeled by error type, so you can distinguish model failures from validation errors from timeouts. A histogram records request duration in seconds, which is how you detect latency regressions over time. The metrics underscore middleware function wraps every incoming request. It records the start time, increments the request counter, processes the request normally, checks the response status code, and increments the error counter if it's 4xx or 5xx, then calculates the elapsed duration and records it in the histogram. The /metrics endpoint exposes all of this in Prometheus's text format, ready for a Prometheus scraper to collect on its polling interval. Once you have metrics flowing, you can build Grafana dashboards that show request rate, error rate, and P95 latency in real time, which is exactly what you need to catch problems before your users do. Completion checklist. While CL module wheat complete, module 8 covered the full arc from raw data to production system. You built a 6-stage training pipeline working through 52,000 examples down to a final 50 example refinement pass. You integrated 4 dataset sources into a unified deduplicated schema. You trained and built system expertise across C, C++, Python, Java, Rust, Go, and more. You applied DPO for safety alignment and hit 100% rejection of dangerous commands in evaluation. You ran 5 test suites and met every target. And in this lesson, you shipped it: Terminal UI, REST API, build script integration, error log analysis, and Prometheus monitoring all in place. The numbers tell the story clearly. Build time dropped from over 60 hours to around 20, a 3x improvement. The failure rate fell from 90% down to an estimated 25%, roughly 4 times better. Query turnaround went from 15 to 20 minutes of manual research down to under 2 seconds. That's a 450x speedup. And perhaps most importantly, the expertise required shifted from senior engineer to intermediate developer with AI assistance. You've genuinely democratized access to this knowledge. The project directory is organized around 2 top-level folders. Under Lessons Malajo 08, the Markdown files walk through each stage in order: problem analysis, dataset integration, training stages, evaluation, and deployment, giving you a written reference for every decision made in code. Under scripts, the numbered Python files map directly to those stages. 01-download-datasets.py fetches your training data, and 06-deploy.py is the terminal UI launcher you ran. The models folder holds checkpoints from each training stage, with the final Linux distro assistant directory being your production artifact. This layout means any collaborator can orient themselves immediately, and any stage can be rerun or updated independently without touching the rest of the pipeline. Next steps. Module 8 is complete. You built a specialized Linux distribution build assistant from scratch, from raw datasets all the way to a monitored, integrated production deployment. Module 9 takes the next step, scaling that deployment with Docker, Kubernetes, CI/CD pipelines, and production-grade monitoring infrastructure. Everything you've built here is the foundation for what comes next. Fascinating. Through careful analysis and practice, you'll master these techniques quickly. Skip wise skippertudes. Take it skippertudes. You'll master these techniques quickly. Wise skippertudes. Mit kostekor. Skip body seva. Skip wamers on Mars. Skippe skamus mother skamus. Skippe one analysis and practice. Zaskip.